Hello, friends. Welcome. This is an introduction to our kind of big project, almost a final project on this unit of waves. And we're going to talk about earthquakes. Now, there's a lot to talk about with earthquakes. I'm actually going to start by talking about an interesting phenomenon that at nighttime, warm air from uh the earth has risen upward, and the cooler, colder air, now that the sun has gone away, is being cooled by the earth and remains low. So we have colder air and warmer air, and of course there's not like a boundary here. There's a steady gradient of cold air to warm air. Now, you might remember that the speed of sound in air is given by this equation and goes as temperature. So warmer air will have a faster sound speed, and colder air will have a slower sound speed, which means this will have a smaller angle and this will have a larger angle. How does that manifest? Well, if somebody is standing here and talking or making a sound, and that sound goes upward like this, then you can sort of think about it. You can imagine there is a boundary at first and say, okay, well, when it hits the warm air, here's the normal line. Here's kind of the boundary between warm and cold. It's going to go outward. So what you can actually do is think about it like this, where there's actually infinite little boundaries, and such that the progression of sound actually curves. So what you would actually observe is if somebody is standing here and talking, and there's warm air up here and cold air down here, what actually happens is the sound wave curves, turns around, and comes back. Because eventually there's going to be a layer here, a normal line here, where you get total internal reflection, where your initial angle way down here, theta 1, is such that your theta 2 here is greater than 90 degrees. And we could probably have a fun time solving for the velocity and thus the temperature difference. But I'd rather focus on a different phenomenon that shares this same characteristic. That if I have steadily increasing sound speed, it's going to curve. Now, you might, so please pause and rewind that, and please be able to conceptually explain why this curves, eventually turns around and comes back down. And of course, if we do a boundary here with the normal line here, this theta 1, right, this theta 2 will be less than theta 1 because the cold air, V cold, is less than V hot. So it's going to curve back down like this. So just going through the concept of how sound speed is affected by temperature, and then how sound speed, sorry, then how angle is affected by speed results in this cool effect. And apparently you can hear this at night. At night, it's easier to hear things over longer distances. In the city, this doesn't really, I think, manifest because there's just so much noise. But in, you know, suburbia, more rural areas, you can hear farther because that sound wave actually reflects off the warmer air and eventually curves back down as a steady gradient. which is kind of cool. So it ends up being this curved path. Okay, so that's step one. Again, please rewind that if you want to review that logic, but the logic's pretty straightforward. Obviously, if we have warm air during the day and cold air at night, pause the video. What do we get? Well, warm is faster, so this will hit a barrier here and will bend outward. Theta 2 will be less than theta 1 because velocity of cold is less than velocity of hot or velocity of warm. So cold here, warm here, it bends up. So therefore we actually get a steady gradient, and we can just say there's a bunch of those little boundaries from warm to cold, and it actually just curves the sound upward. Isn't that kind of cool? That the path of the sound actually changes as a gradient. So that's step one. Ooh. Did that kind of was that kind of cool? Right? It kind of it tickles the curiosity bone, right? So we get a steady gradient of velocities resulting in a steady gradient of angle, thus a curving line in one direction or the other. Awesome. All right, you ready for part two? This is gonna be cool. All right, so without going into the details of earthquakes, earthquakes have two waves. There's called P waves and S waves. There's also love waves and Raleigh waves. I kind of want to talk about those, but that takes a minute. And I'd rather just look at P waves, which are compression waves. They're basically sound through the earth. They're the primary, P for primary, S for secondary. They're the primary, um, highest amplitude, highest energy earthquake. Primary, right? They are the earthquake, right? Although all four of them combine to, cause the disruption and destruction that are associated with earthquakes. P waves are sound to the earth. They are compression. The S waves are actually transverse. They're kind of like this, but the compression lines that you guys have mostly been drawing pretty well, that's what we're going to focus on. So if you look at P waves, like say an earthquake happened here, it would send waves out in all directions. There would be one going down, there'd be one going this way, there'd be one going this way, there'd be one going this way. They would go along the surface of the earth, but also through the earth. So what happens to those sound waves? What happens to those earthquake vibration waves as they go through the layers of the earth? Something remarkable happens. There's so much power in them. There's so much vibration. Again, you can say there's so much energy, but the vibration, that frequency, that amplitude is so strong that it actually propagates through the entire earth. This one will just go straight through the earth and eventually be felt in Australia. I think it takes about half an hour or 90 minutes. I'm going to ask you guys to calculate that at the end and just sort of marvel at how long it takes to go through. But if you have a seismometer in Australia, it would feel an earthquake that happened on the other side of the earth. And so there are seismographs all over the earth. And so every time there's an earthquake, there's a delay, and they are felt in other places. And it turns out that you can get a surface wave running across, and you might feel it in Greenland a certain time later, but then it's actually felt again from underneath in the same location. And it's also felt here. And there is nothing felt here. This is called the shadow zone. That's kind of a cool name. The earthquake shadow zone for P waves. Nothing. Ah, nothing is felt in a certain range here. What does that mean? Well, you can put all the information from all the seismographs. Say there's an earthquake somewhere in Alaska, in Siberia, in Brooklyn, wherever it is. It'll go through the earth and it'll appear in these locations. And there's seismographs everywhere nowadays. And you can put that in a supercomputer and it can just relay back, well, that means the path had to be this because there was a delay. So you can calculate the time it takes. And it turns out this path bends like this. What? Obviously, if we have 0 degrees here, it's going to be 0 degrees here. It's going to be 0 degrees here. It's going to be 0 degrees here, 0 degrees here. So all of our normal lines are like that. But here, the normal line is like this. Here, the normal line is like that, right? In this layer, the normal line is like this. So we have a non-zero angle and we get refraction. So how earthquakes refract through the earth teaches us about the layers of the earth. This is how we know what the earth is made of. There's other information that helps us. Its rotation, its mass, therefore its density, the fact that it has a magnetic field, all support what this also shows. But earthquakes are literally like again, they're like a fingerprint. They reveal the bulk modulus and density every layer down into the earth. It's like an X-ray of the earth. So how do we know what the earth is made of? Earthquakes, which is absolutely extraordinary to me. And you guys have an assignment, which is to look at the past. So this is actual data. If an earthquake occurs here, this is how the paths move through the earth. You might see a mini shadow zone here. We're not going to really go into that one. This one's the main one because it's caused by this refracted angle into the outer core. This is called the mantle. You might have heard of that. This is the outer core. This is the inner core. This is the layers of the earth. I'm always surprised at how big the core is. I always felt like the mantle should go deeper in, but it doesn't. It goes about little, honestly, not even halfway. So if 0 is the center, the radius, the farthest radius of the Earth is about 6,400. Oops. Where are we here? There we are. That's what I wanted. Is that about 6,400 kilometers? So this right there is 6,400 kilometers. It's actually 6,371 kilometers, but rounding, we're going to call it 6,400. And at each layer down, we go to a smaller radius, and you'll notice that these sound rays curve. And so focus on the section around 6,000 kilometers. Normal lines at each section are radii toward the center of the Earth. Redraw this section close up. So I'm not going to redraw it right now, but this is just a warm-up, by the way, right? And there's a bunch of questions you're going to go through, but I wanted to go through this for those who are missing class on Monday, because this is what we're going to go over on Monday, is how to draw this. So this path here, for example, see that one right there? And maybe this path here, right? And then maybe this one here. That's curving up. What does that look like? Well, that's like the warm air, cold air thing. Ooh. So we have a gradient of velocities because now we have a gradient of angles. That's kind of cool, right? So if I draw just this line here, right? Here's the surface of the Earth, and here's like a boundary deeper in. Then I have some normal line here. I have some normal line here. So I have some angle theta 1 here, and I have an angle theta 2 here. And theta 2 is clearly bigger than theta 1 as you go deeper and deeper down. What happens to the angle? It grows, which means what happens to the velocity, which means what happens to the bulk modulus and the density. What's happening in the mantle to cause this speed change, to cause this angle change? I'll repeat that because that's like the most important point. What is happening in the mantle? What causes V to change with depth, which then causes angle change that we observe? So the physics goes like this. The composition of the mantle clearly changes as you go deeper. What changes? The angle of the earthquakes reveals that. The angle is the outcome, right? The change we observe, right? That's the outcome. That's actually the last thing, right? This is the outcome, right? This is the end result, right? Because if you remember, like bulk modulus, density create velocity, which creates angle. So we observe this, but we're going to think backwards, right? And use that logic backwards to determine the speed and determine, therefore, bulk modulus density. And then start to think about what's causing that? What's causing this to change in the mantle? And thus we literally can peer into the earth with earthquakes, which I think is just absolutely extraordinary. So that's what you guys are going to do. Please understand this logic right now. That's my quest for you today, is just to understand this logical progression. This is the order of logical progression. This was my goal. The rest of the assignment we're going to work on, it's due in a week. And you're going to do some math. You're going to figure out the velocity at all these different points, at all these different radii. You're going to graph it. You're going to explain the precise curvature and the physics that creates that. You're going to figure out the angle at which all of those leaves. I'll give you a hint. It's just like total internal reflection, like I was just talking about with the warm and cold air. And you're going to explain the physics of why they turn around, what's happening in the mantle. And then let's not forget this big jump here. Bakatoom, what's going on there? That's like actually the most important part. So we're kind of creeping into the mantle, which we should not ignore. But then this in the outer core ends up being a really, really big deal. So I'm going to pause. That's my introduction. Right now, you can focus on a point in the center of your head. Draw a line to your heart. Feel your heartbeat. Feel vibrations go through your body and how you, in feeling those vibrations, can sense every part of your body at once. And then see if you can visualize revealing the entirety of the earth at once. That takes a little more, but give it a try. And that you and the earth are manifested and revealed through these vibrations. I think that's pretty cool. Stay there. Stay there as long as you can. Namaste.